Welcome to Cambridge IGCSE Physics, Lesson 60.1, Gravitational Field Strength Variation. Today we explore how gravity changes with planetary mass and distance, fundamental concepts for understanding gravitational fields. Let's examine our learning objectives for today. By the end of this lesson, you will be able to know gravitational field at surface depends on planet mass, meaning larger planets have stronger surface gravity. No field around planet decreases with distance. Gravity weakens as you move away from the planet. Understand gravity gets weaker further away. This explains why astronauts experience weightlessness in orbit. These objectives align with Cambridge IGCSE core content requirements. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, gravitational field, which means the region around a massive object where gravitational force acts on other masses. Second, surface gravity, which means the gravitational field strength measured at the surface of a planet or moon. Third, mass dependence, which means that gravitational field strength increases when the planet's mass increases. Understanding these terms precisely is crucial. We measure gravitational field strength in newtons per kilogram, written as N per kilogram. Let's explore our first core concept. The fundamental principle states that gravitational field strength depends on planetary mass. This means planets with more mass create stronger gravitational fields. The definition is, gravitational field strength equals force per unit mass. Mathematically, we express this as G equals F divided by m, where G represents gravitational field strength measured in newtons per kilogram, F represents gravitational force measured in newtons, and Sm represents mass measured in kilograms. The diagram illustrates field lines radiating from a planet. Notice how the larger planet has stronger field lines than the smaller planet below. This principle is fundamental because it explains why different planets have different surface gravity values. Now we examine how distance affects gravitational field strength. This follows a fundamental physics principle. The key principle states that field strength decreases with distance from the planet. At the surface, we measure maximum field strength because this is the closest point to the planet's center. Moving away from the surface, field strength decreases rapidly following an inverse square relationship. At far distances, the gravitational field becomes very weak but never completely disappears. For example, Earth's surface gravity equals 9.8 newtons per kilogram, but astronauts in space experience much weaker gravity. The diagram shows concentric circles representing different distances, with arrow thickness showing field strength decreasing outward. Let's work through our first example. The problem states, calculate gravitational field strength when a 5.0 kilogram mass experiences 49 newtons force. We are given mass m equals 5.0 kilograms and force F equals 49 newtons. We need to find gravitational field strength G. Step 1. Write the equation. We use the gravitational field strength formula, which is G equals F divided by m, where G is field strength, F is gravitational force, and m is mass. Step 2. Substitute the values. We write G equals 49 newtons divided by 5.0 kilograms. Step 3. Calculate. 49 divided by 5 equals 9.8. Step 4. State the answer. The gravitational field strength is 9.8 newtons per kilogram. This value equals Earth's surface gravity, confirming our calculation is reasonable. Example 2 applies comparison analysis between planets. The problem is, compare gravitational field strengths of different celestial bodies. The data shows Earth's surface gravity as 9.8 newtons per kilogram, while the Moon's surface gravity is 1.6 newtons per kilogram. Now we analyze. First, calculate the ratio. We divide Earth's gravity by Moon's gravity. 9.8 divided by 1.6 equals 6.1. Second, interpret the result. Earth's gravity is 6.1 times stronger than the Moon's gravity. Third, draw conclusions. This significant difference explains why astronauts can jump much higher on the Moon. Fourth, explain the reason. Earth has much greater mass than the Moon, creating stronger gravitational field. The bar chart shows this comparison visually, including Jupiter's even stronger gravity. Mathematical skills are crucial in gravitational field calculations. Let's examine 3 key skills. First, equation rearrangement. When we need to find a different variable, we rearrange algebraically. Starting with G equals F divided by m, which defines gravitational field strength, to find force F, we multiply both sides by m, giving us F equals G times m. This rearranged equation lets us calculate gravitational force when we know field strength and mass. Second, unit handling. Gravitational field strength uses newtons per kilogram, but can also be expressed as meters per second squared. Both units are equivalent. Third, significant figures. Your final answer should match the precision of the given data. If measurements have two significant figures, your answer should also have two significant figures. Now practice what you've learned with these three questions. Question 1 is basic level. It asks, a 2.0 kilogram mass experiences 20 newtons force. Calculate the gravitational field strength. Use the formula G equals F divided by m. Question 2 is intermediate level. It states, on Mars, gravitational field strength equals 3.7 newtons per kilogram. Find the gravitational force on a 60 kilogram astronaut. This requires you to rearrange the equation to F equals G times m. Question 3 is advanced level. The question asks you to compare gravitational effects between Earth and Moon surfaces. This tests your analytical skills and understanding of mass dependence. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Gravitational field principles power modern space technology. Let's see how today's concepts apply in practice. In space exploration, engineers calculate fuel requirements for landing on different planets by considering their gravitational field strengths. Mars missions need less fuel for landing than Earth return journeys. In satellite technology, understanding how gravitational field varies with distance enables precise orbital calculations for GPS satellites and communication systems. In engineering, structural designers must account for local gravitational variations when building bridges, skyscrapers, and other large structures. These applications show why gravitational field knowledge matters. Career-wise, this physics leads to aerospace engineering designing spacecraft, astronomy studying planetary systems, and geophysics monitoring Earth's gravitational variations. The concepts you learn today become tomorrow's space missions and technological breakthroughs. Let's review the solutions. For question 1, the answer is G equals F divided by m equals 20 newtons divided by 2.0 kilograms equals 10 newtons per kilogram. This is reasonable as it's close to Earth's gravity. For question 2, we use F equals G times m equals 3.7 newtons per kilogram times 60 kilograms equals 222 newtons. This is much less than the astronaut's weight on Earth. For question 3, Earth's gravity is 9.8 newtons per kilogram. Moon's is 1.6 newtons per kilogram, giving a ratio of 6.1 to 1. Now, exam success tips. First, always show you're working step by step. Even if the final answer is incorrect, you earn marks for correct method. Second, include units in every calculation step. This is essential for full marks. Third, check if your answer is reasonable. If you calculate negative gravity, something is wrong. Fourth, understand command words. Calculate means find a numerical answer with working. Explain means give scientific reasons. Let's summarize today's lesson on gravitational field strength variation. The key points to remember are, first, gravitational field strength depends on planetary mass and is measured in newtons per kilogram. Larger planets create stronger gravitational fields at their surfaces. Second, gravitational field strength decreases rapidly with distance from the planet's surface, following an inverse square relationship, which explains why astronauts experience weightlessness in orbit. Third, calculations use the formula G equals F divided by m, which can be rearranged to find force or mass when other quantities are known. These three concepts form the foundation for understanding gravitational fields and orbital mechanics. For further study, review the definitions of gravitational field and field strength. Practice problems comparing different planets' surface gravity. The next lessons will cover orbital motion, which builds on today's work by explaining how gravitational field variation enables stable satellite orbits. Ensure you understand today's concepts before moving forward, as gravitational physics builds systematically.